Oh, this is fine, I think. Hello. Yes. Hi, everyone. Today we're talking about relating structure and power using game comonads and with the subtitle of Towards Generalizations of Modal Logic. I'm Richie, Selena, Tyler, Jishwan, our teammate, is attending virtually, and we would just like to thank Dan and Nihil for being our mentors and TAs.
All right, let's get into it. So briefly, we're splitting this talk into sort of quick background material for people who have never seen this stuff before, and then we're going to talk about what we specifically did during the week. So we need to ask these questions. What is finite model theory and why do we care about it? These are two important questions to answer. So very loosely, finite model theory studies the expressive power of logics on finite structures. So these are things like finite graphs, databases, structures of interest to people like computer scientists, because computer scientists represent things in finite ways. So get some quick preliminary definitions out of the way so we can move on. So we talk about these relational vocabularies. Sigma is just a collection of relation symbols. Each of them has an associated arity. And then once we have fixed some vocabulary, we can talk about structures in that vocabulary. So a sigma structure is just a universe, which is a set, and an interpretation of every relation symbol in our vocabulary as an actual k-area relation on that set. So for example, you can think of graphs as sigma structures where you take sigma to be just a single binary edge relation. So how do we actually tell if two structures are the same in some logic that we're interested in studying? Well, the answer to that question is we play games on our structures. So specifically, we play these types of games called spoiler duplicator games. So you have two players. One player is the spoiler. Their goal is to show that two structures are different. And the other player is the duplicator. They're trying to say, no, these are the same structures. So, you know, the change my mind bro here is the duplicator. They're trying to say that this obvious deer is actually a horse. The spoiler, unfortunately, doesn't know the word horn. So this is sort of analogous to the spoiler not having the expressive tool in their logic to differentiate a horse from a deer. And so sort of formally, we can say, well, a structure A is equivalent to B in some logic L. We can define that as saying, well, if for every formula in our logic, A entailing that formula bidirectionally implies that B entails that formula. And so a specific example of one of these games that is really important for us is this game called the Ehrenfeucht-Frasse game. I'm not going to pronounce that anymore. I'm just going to call it the EF game from now on. So the reason why this EF game is important is because there's this theorem that basically says if you can show that two structures are equivalent, or if there's a duplicator winning strategy in the K-round EF game, that's equivalent to the structures agreeing on first order logic formula up to quantifier rank K, meaning like, you know, you have your four alls and your exists and K of those. Not actually K quantifiers, but quantifier rank. And so this third condition here might be striking a little interest, which is that this third equivalent condition is also that there is a co-Kleisli morphism from EK applied to A into B. So that's what we're going to be talking about now. So basically, this game Comonads project is about comonadifying these model comparison games. So EK is a comonad on the category of sigma structures. So basically what that means, well, we need to take a sigma structure, A, and we need to construct a new sigma structure, EKA. How do we do that? Well, we need a universe for this new sigma structure. This universe, basically, we just take A to the set of spoiler plays. So these are like non-empty sequences of elements of A up to length K at most. And then the co-unit of this comonad just returns the last move of a play. And then we can also define how it acts on relations and also this co-Kleisli lifting operation, which are we're not going to talk about too much in the interest in time. But then, so the question is, how do these actually encode one of these model comparison games? So we can think of a function from EKA to B as sort of like a duplicator response to any given play that the spoiler can make, right? So like given some sequence of plays in A, the duplicator gives an element of B. So we can think of these as like duplicator strategies. And then the fact that F is a homomorphism of structures means that it has to preserve relations. And so in particular, the way that the comonad acts on relations implies that the duplicator strategy is actually winning. So this is why there existing this co-Kleisli morphism is equivalent to there being a duplicator winning strategy in this game. And then the co-extension is just sort of modeling the history preservation of the game. So, oh, right, yeah, forgot to mention. So we can like sort of read off from this definition what this actually means in terms of a game, right? So basically the way this game works is the spoiler picks an element of A, the duplicator responds with an element of B, and then the duplicator wins if after K rounds, the chosen elements form a partial isomorphism between the two structures. So we kind of figured, since this is a category theory crowd, we would present the comonad first and then tell you what the game was. So up to you whether that was successful or not. So yeah, turn it over to Richie now.
Thanks, Tyler. So yeah, we talked about these game comonads, and it's great. But why are we actually interested in them besides being at ACT, right? So the first reason we care about these game comonads is because it gives you like a way to capture these different model comparison games in a single abstraction. So it's a more uniform way to look at these things. Because if you look at the games descriptions themselves, they all look very different. But when you turn them into comonads, they're going to have the same sort of algebraic structure, right? So that's the first reason. The second reason is once we have these game comonads, we can start looking at the coalgebras of the comonads. And it turns out that these coalgebras of the comonad, specifically for EK, they correspond to some combinatorial property. So if you take the K, the index of the comonad, that K corresponds to the tree depth of something that is called the tree cover of the Geifman graph induced by the sigma structure of A. And if you can do the same for other comonads. So here we have the pebbling comonad and the modal comonad, which we don't have time to get into, but they correspond to the tree width and the synchronization tree depth respectively. Yeah. Oh, no, yeah, that's fine. Go back. So yeah, as a quick recap, that was kind of the background of finite model theory and game comonads. And then now we're going to talk more about what we actually did in this research week, which is applications to modal logic generalizations. So what are we doing? So first order logic, most of you know what first order logic is. It's very useful for encoding your problems. Most of your problems in life can be turned to a first order logic thing. So that's good. But now if you want to study your thing as a first order logic formula, and you ask questions like, is this formula always satisfiable, or is it sometimes satisfiable, or is it never satisfiable? These sort of things, the SAT problem of this logic is undecidable. So there's no algorithm that can decide it in finite time all the time. On the other hand, there's this other logic called modal logic, which is not as expressive as first order logic, but is robustly decidable. So it can be efficiently checked whether it is a statement is sometimes true, always true, and so forth. And it turns out you can view modal logic as a fragment of first order logic. So we have this thing that is powerful, but we can't prove things about it, and we have this thing that is less powerful, and we can prove things about it. So the question is, can we extend this weaker thing, modal logic, to something closer to first order logic without losing the SAT property? And the answer turns out to be yes. And we're going to study these two fragments called the unary negation fragment of first order logic and order fragment of first order logic. So we're going to find games and game comonads for them. So the first fragment, the unary negation of first order logic, looks pretty much like the first order logic. And you can see kind of its signature. This is how you define it. You have variables, you have relations on these variables. You can do disjunction and conjunction of the formulas. You can do existential quantifiers, equality. And the only catch is when you do negation, you can only do negation on formulas with at most one free variable. And a consequence of that is because you can build the for all using existential quantifier and negation, you can only do for all on formulas with at most a single free variable, and which is limiting. Another thing you can't do is you can't apply negation to x equals y because there's two free variables, right? So that's another restriction that is not very great. We'll talk more about that later. So here's a property you can express. You can express that these vertices form a cycle, full cycle, I think. And then
that was the last R is supposed to be an E.
Yeah. But a free cycle actually, and then this other property you can't express because there's free variables and there's two of them and you're negating it, so you can't express that.
Okay, so we've talked about games. So what's the game for the uniform logic? So this is the one that is given in the paper where these logics are introduced. The idea is we have two structures, as usual. We have a starting position, which is an element of A cross B. And then spoilers chooses a structure. Let's just say A for because it's easier. And then chooses a finite subset V of A. And then the duplicator needs to find a partial homomorphism defined on V such that the image of A is B. So we have a pair that we have to keep. And then once the duplicator has done that, the spoiler chooses another element of V and fixes a new pair. And then we restart. So the duplicator wins on a K round if such a partial homomorphism can be done. So if they can go through step 3 of this. And now the thing is, this game is really nice, but it doesn't have the same structure as the other games that we have, which means that it would be a little harder to find a comonad for it. So the first thing we did was find an equivalent game that was closer to things that we have in the literature. So we will have the Pebble UNFO game. And the idea is we have two structures. Spoilers chooses one of them. And as long as we stay on the same structure, the game goes exactly like in the EF case. So spoiler chooses an element of A, duplicator chooses an element of B, and we go on and on and on. And the problem is, the moment spoiler chooses to change structure, so to go to B in this case, they will choose one play and forget everything else we've done until now. So we kind of clean the board. And then the game continues as in the EF case. And the duplicator wins a round if the current board, so not talking about things we've forgotten, forms a partial homomorphism. Now there's a variant, slight variant of this, where instead of letting spoiler choose a play, we just keep the last play and forget everything that happened before that. And we have mostly proven that these two versions are equivalent to the original UNFO game. And we'll have an example of this, and because it was Richie who found this example, I'm going to let him do it.
Yeah, thanks, Elena. So we're going to use the games that we shown earlier to be equivalent to the original UNFO game to actually prove something, right? So we're gonna walk through the utility of these model comparison games. So we're specifically gonna prove that this property that I've expressed here in first order logic can't be expressed in the unary negation fragment. So how does this work? We have two structures, A and B. And these edges represent binary relations, so B and R respectively, blue edge, red edge. And you see that the structure A satisfies this property where there is a pair such that there is a blue edge, but no red edge and no orange edge. But B doesn't have that, because for every pair of vertices, if you pick the vertex twice, there is both a blue edge and an orange edge. So A satisfies it and B does not. But you can't win this game, the UNFO game. So it turns out there's no UNFO formula that can distinguish these two things. So therefore, this property can't be expressed. So as Tyler said earlier, like they know what a horn is. Like, this is our horn. Like, you see. Okay, so this is how the game works. The spoiler is going to play on the side A because it's the more interesting side. Let's say they, without loss of generality, choose A1, that vertex, and then duplicator is forced to choose B1. And you see at all times, there is a graph homomorphism from A to B, right? You can see that this subgraph is the same as that subgraph, obviously. And after that, the next step would be the spoiler would choose the other vertex, because that's the more interesting thing to do. Like, you can check the other cases as well. And the duplicator is forced to choose the same vertex on their side again. And you see there is still a graph homomorphism between A and B, the subgraph induced by these vertices A and B. Specifically, if you see A1 and A2, that edge is still preserved in that relation. The fact that there is an orange edge, it doesn't matter, because we just need to preserve relations and not reflect them. And the extra thing about the game is the spoiler can switch sides on the board, and they can now play from B, but they have to discard all but one set pair of vertices, right? So now they're playing from B, and they have B2, and B2 corresponds to A2. And you can see, obviously, there's still a graph homomorphism between these. So, and now if they play B1, if they play B1 now, they're going to play A1 on the same vertex, and this game becomes really boring. So you can see there's no way to tell these two structures apart in UNFO. Therefore, this property can't be expressed, because that would tell them apart. Yeah.
Thank you. So we are an applied category theory conference, so we need category theory at some point. So coming back to the Comonads, if you've been following, you've been reading the slides, you probably have noticed that the EF game that we've mentioned gives us formal, like a first order logic, existence of first order logic. And that's because the game we were playing, we were forcing the spoiler to play on one side the entire time. So the way to find a construction that gives us the equivalence on first order logic period is to use this. So I'm going to wave my hands a lot on this part because we do not have time to explain all of this. But the idea is, on the category of co-algebras in EK, we have this thing called open pathwise embeddings. And if we have a span of open pathwise embeddings, a duplicator winning strategy is the same as having one of these. The idea is basically that we can go from A to B and from B to A without losing any kind of information, because the open pathwise embeddings let us keep all the relations when you go back and forth. And the thing is, the UNFO game, we do lose some information. So how do we encode that? The idea we have is have two spans. So the idea is, whenever spoiler is playing on A, we are on the first span. So we can go from A to B without losing information, but not from B to A. And then the moment a spoiler goes to B, we go to the other span, in which we can go from B to A without losing information, but not the other way around. Now the thing is, we need some kind of condition to link these two spans, and that is work in progress for now. And now the other logics we've been working with are the order fragments. So these are pretty much first order logic. The only things that we do is, in relations, we force the variables to only appear in the order they've been introduced. So we have these 3 different variants. In the prefix fragments, we have to start on the first variable and then go over. In the fluted fragments, we have to go all the way to the last variable. And the infix fragment, just as long as they are in order, we're good. So you have some examples in case you need some kind of idea.
Yeah, so I know we're almost out of time. So basically, I'll just quickly mention the comonadification of these ordered fragments. So we basically did manage to find comonads for all 3 of these fragments. They essentially boiled down to being small modifications of the original EF comonad, where you just tweak what it's doing on relations. And then looking at the coalgebras was interesting because essentially what we found is that the existence of a coalgebra for each of these comonads corresponded to the structures that they're looking at being different types of forests of certain heights. So like one of them was a directed forest, one of them was an undirected forest but allowed 1 cycles, things like that. So yeah. Ongoing work, there's obviously a lot still left to do. So the first thing we need to do is extend these ordered comonads to allow variable rebinding, because we didn't capture that part of the logics. And the other thing is, we waved our hands about these coherence conditions. We have some ideas of how to do this, but we need to actually formalize them a little bit better. So yeah, that's game Comonad.
Okay, thank you, Elena, Richie, and Tyler. That group was mentored by Dan Marsden. Does anyone have a question for them? Okay. If not, then let's give everybody in the Adjoint School a round of applause. Thank you so much for attending this session. Okay, we can break for